So we've been solving linear, second-order, constant coefficient, homogeneous differential equations. We've been solving equations of this form where this g of t part was equal to 0. Now we want to solve the equations when this g of t part is not equal to 0. It's some other function of time. Let's start with this example here where the function, the g of t, the target function, I'm going to call it the target function, is 8. Now, I know I can find the homogeneous solution to this one. If I look at this and I think about the auxiliary equation is going to be lambda squared minus 3 lambda plus 2. Your eigenvalues are going to be 1 and 2. Your homogeneous solution is going to be some constant e to the t, some constant plus some constant e to the 2t. We can solve this homogeneous equation. If I put that homogeneous equation in, let's in fact just write it out instead of talking about it. It's going to be, that's our homogeneous equation, our homogeneous solution. If I put that into the left-hand side, and by put it into the left-hand side, I mean I need its first derivative, I need its second derivative, I take its second derivative minus 3 times its first derivative plus 2 times itself, 0 is going to come out. I need something then to add to this solution so that 8 comes out. This won't do it. If I put this in, 0 comes out. If I put this into the left-hand side. So I need what we're going to call then a particular solution, and its only job is to hit the target function. I just got to have something where that, what I guess, 2 times that, what I guess here, minus 3 times the derivative of what I guess here, plus its second derivative of what I guess here equals 8. That's what I'm looking for. Now, if I think about it for a minute, and you can pause the video and think about it. Okay, you thought about it, or you didn't, and I'll think about it for you. It looks like we can just guess a constant because the constant or the target function is a constant. If I do that, then the particular, this derivative of the particular solution is equal to 0, and its second derivative is equal to 0. And if I sub all these three things in, I'm going to get 0 minus 3 times 0 plus 2 times a is equal to 8. That means a must be equal to 4. Now, if you honestly did pause it and work it out on your own, that's the sort of thinking that you did in your head, adjusting. But what we did was guess a solution of the form with a coefficient we didn't know. The method's going to be called unknown coefficients. The a was the unknown coefficient, and then we figured out what the a had to be, such that when I plugged it into when I plugged the particular solution into the left-hand side, into the y prime prime minus 3y prime plus 2y, I got 8 out. So our general solution, our whole solution, the solution, is going to be equal to our homogeneous solution plus the particular solution. So in our case, our general solution is going to be the homogeneous solution plus the particular solution. Now there's some questions. Well, let's answer the questions first. One of the questions that I might get here is, well, what do I need this? I want to solve this differential equation, right? It was equal to 8, and the 4 does it. Why do I need this homogeneous solution in the first place? What does it do? It goes into the left-hand side and it produces 0, produces nothing. Why even bother? Why can't I just say the solution is 4? That solves the differential equation. Yes, it fits into the differential equation. I would verify that it is a solution. But if you give me a second-order differential equation, coming with that second-order differential equation might be 2 conditions, might be two initial conditions. I get two constants. There's the answer to that question. What's the homogeneous part for? It has the constants in it. If I just said y is equal to 4 and I left it at that, I couldn't meet any initial conditions other than y naught is equal to 4 and y prime is equal to 0. Any other initial conditions I can't meet with just that solution. So the purpose of the homogeneous solution is to have the constants in it, so I can dial in the values of those two constants to satisfy initial conditions. The purpose of the particular solution is just to hit the target function, so it doesn't need any constants. We're going to learn two different methods for getting the particular solution. So that's what I need here, right? If I'm trying to solve a linear second order constant coefficient non-homogeneous differential equation, then I need to find the homogeneous solution first because it has the constants. We already know how to do that. I need to then just add to that homogeneous solution a particular solution. So we're going to learn two different ways of getting that particular solution. The first way, the subject of this video, is the method of unknown coefficients, where we kind of guess a form of a solution, but we leave some of the constants as unknowns, the unknown coefficients, and then we plug it into the left-hand side, set it equal to the target function, and figure out what those unknown coefficients have to be such that the particular solution really is a particular solution to the differential equation. Now, students don't like this, in my experience, don't like this technique for the reason that it has a little bit of what they feel as guessing in it. And I guess it sort of does, but it's not just wild guessing, it's educated guessing, it's thinking guessing. So they still don't like it because some people want to view math as a series of steps, and differential equations fits into this viewpoint a lot, where this is the type of problem I do steps A, B, and C and solve. Unknown coefficients, though, yes, at the beginning it seems kind of a little arbitrary, so you're uncomfortable with it. The second method we're going to learn, variation of parameters, next video, seems, wow, he's going to give me a formula, I'm going to follow through this formula, Betty Crocker, and boom, I'm going to end up with an answer. Yes, but variation of parameters, there's some integration in it, as you'll see it in the second video, and it's long. It takes a long time. It's hard to figure out. Unknown coefficients, when it works super well and is very quick. We got that 4 really fast. Solve the solution. Solve the non-homogeneous differential equation. So it's a good method, but it hinges on you making a good guess to hit your target function g of t. Let's see another example with trig. Here's our y prime prime plus y prime plus 2y equals. Now I need to solve it. So I need to solve my homogeneous equation. So our steps are going to be first solve the homogeneous equation. So in order to do that, I'm going to need my auxiliary equation. So I'm just solving this like we did in the past 3 videos. This one's going to be complex conjugate roots. There are my eigenvalues. I knew the real part of the eigenvalue was going to be negative because all the coefficients, the 1, and the 2 are positive, so I knew the real part was going to be negative. Now I've got my complex conjugate eigenvalues. Let's write out our homogeneous solution. So here's our homogeneous solution. We could figure out the period, 2 pi divided by the b and that, but we're done. The two constants, the a and the phi, I could figure out if they gave me initial conditions, but they don't. So we're done. There's the homogeneous. Next step is then get the particular solution, and we need to figure out a guess to hit our target function. Now take a look at our target function. Our target function is 2 trigs, 2 trig 2t's. So I'm going to guess some linear combination of sine 2t's and cos 2t's. Now I'm not guessing that just because it had both sine and cos. Even if it only had one of the trig, I would still guess a linear combination of 2, because when I differentiate, if I just pick the sine, when I differentiated it, and I will because it has to go in here, it would make its own cosine. So cosines and sines are going to pop up from the derivatives. So this is going to be my guess. Now I need, well, that'll go in here. I need its first derivative and I need its second derivative. So let's differentiate these pieces. So we've got our derivatives. We're going to sub the derivatives in the left-hand side and make it equal to the right-hand side and figure out what constants a and b, what the coefficients a and b have to be. So when I sub it into the left-hand side, I need one second derivative plus one first derivative plus 2 of the original function and I'm making that equal to the target function. Now I got to just simplify this, clean this all up. Simplify this, clean this all up. That means group how many sines on this side, group with the sines, group with the cosines on the left-hand side. So let's group with the sines. I have minus 4a here. I have minus 2b here, and I have 2a here. That's all. Those are the coefficients of the sine 2t. Plus the coses. I have a minus 4b here. I have a 2a here, and a 2b here. Equals the target function. So I can see the coefficient in front of the sine is 8. So then this bracket must be equal to 8. The coefficient in front of the cosine is minus 4. So this bracket must equal to minus 4. So I've got two equations, two unknowns. Just solve them. There's the two equations. Simplify them. I get a is equal to minus 3 and b is equal to minus 1. So our particular solution then is minus 3 sine 2t minus cos 2t. So our general solution, so subscript general, the whole solution, is equal to the homogeneous solution plus the particular solution. And at this point, at the very end, if they had given me initial conditions, then I would sub them into this the general equation to try and figure out the initial conditions. Let's do another example. So here I've got an equation, and you'll notice in these two, well, let's look at this example first. I've got y prime prime plus 3y prime plus 2. I want to solve it, so I need the step 1 is get the homogeneous solution, and the homogeneous solution, my eigenvalues are going to be the roots of lambda squared plus 3 lambda plus 2. I can see that my eigenvalues are going to be minus 1 and minus 2. So lambda is going to be minus 1 and minus 2. So my solution is, and no surprise that the eigenvalues are negative real part because all of the coefficients are positive. So here's my homogeneous solution. Now I need to get the particular solution. Well, let's guess a particular solution that when I the second derivative of it plus 3 times the first derivative plus 2 times is equal to 3 e to the 4t. I guess that some constant e to the 4t is a good guess, because every time I differentiate something constant e to the 4t, I get some number e to the 4t. This will be some linear combination of e to the 4t is equal to 3 e to the 4t. I can figure out what the a is. That's a good guess. So I need the derivatives. The first derivative would just be 4a e to the 4t. The second derivative would be 16a e to the 4t. So I can sub these, the y particular, the y prime particular, I can sub all that into the left-hand side. So I'm going to get y prime prime plus 3 times y prime plus 2 times y prime, and that's equal to the target function. I'm setting it equal to the target function. And now all I have to do is figure out what a is equal to. Well, that's going to be 16 of these plus 12 of these plus 2 of these. 16 plus 12, 20. That's going to be 30a is equal to, there's no a in front, is equal to 3. So it looks like the a has got to be a tenth. That's our unknown coefficient. So then our particular solution, so don't just end on, oh, a is a tenth. Yeah, it is. But our particular solution is 1/10 e to the 4t. So our general solution, the whole solution, the complete solution, however you want to say it, is going to be equal to our homogeneous solution that has the constants in it, plus our particular solution whose only job is to hit the target function. The homogeneous solution, its job is to hit initial conditions if 2 initial conditions were given. Our particular solution is, its job is to hit the target function. So now we solve this equation. Let's do another example. This new example, well, it's a new example, but it reuses the differential equation part. I'm only changing the target function. So the particular solution is the only new thing I need. The homogeneous solution will be the same because the homogeneous part of the equation, the differential equation part, is the same. So these two examples have the same homogeneous part. So the only new thing to do now is get a new particular solution and add it to this same homogeneous solution. So the target function is 3 e to the minus 2t. So a good guess then, is going to be, why don't we let it equal to, 4t worked last time, so minus 2t, that seems like a good guess. Now I need its derivative and its second derivative, so I need y prime. So here, my guess, my first derivative of my guess, my second derivative of the guess, sub these into the left-hand side of the differential equation, make it equal to the target function. So I need the second derivative plus 3 times the first derivative plus 2 times my guess equal to, and now just figure out what a is. When I simplify this though, I get 4 of these a with these a to the 3 or e to the minus 2t. I get 4 of them minus 6 of them plus 2 of them. That equals 0. They all cancel out. So I can't figure out what an a is to hit this target. What happened? It worked so well in this first example. Well, what happened was minus 2 was an eigenvalue. Oh, so yeah, no surprise when I subbed e to the minus 2t in, with minus 2 being an eigenvalue, it's no wonder that when I subbed a multiple of it into the left-hand side, into the homogeneous part of the equation, 0 popped out. That's how we get the eigenvalues in the first place. So this is, long story short, not a good guess. So I need to guess something else. Well, what happened last time when I needed a something else? Last time when we needed a something else when I had real and repeated eigenvalue, I threw another t in front. So I'm going to do the same thing. That's going to be my guess. So when this is an eigenvalue, I guess the next level of complexity up. I threw a t in front because it worked last time. If it works again, then it's a good thing. Remember, the particular solution, it's just a solution, a particular solution. It just has to hit the target. That's it. However I get it is irrelevant. So let's guess a t e to the minus 2t. I need the first derivative and the second derivative. So I have the two derivatives now. So I'm subbing it into the left-hand side of the differential equation. So I need the second derivative plus 3 times the first derivative plus 2 times the guess is equal to the target function. And now see if we can figure out an a that works. You'll notice there are two types of algebra on this left-hand side. There are pieces with a TA and pieces without a TA. Let's look at the pieces with the TA. There's 4 of them here, minus 6 of them here, plus 2 of them there. Yeah, they all cancel out. So I'm canceling out these pieces all cancel. And now I get minus 4a plus 3a, that's minus a. So I get minus a e to the 4t, no, e to the minus 2t is equal to 3 e to the minus 2t. So a's got to be minus 3. So our particular solution is equal to minus 3t e to the 2t. So our general solution is going to be equal to our homogeneous solution that has the constants in it to hit initial conditions if given, plus our particular solution, whose only job is to hit the target function. Solved. Because this technique of unknown coefficients involves a little bit of guessing on your part, practice is very important. So it isn't just like the second technique, which also requires you to do your homework and practice, but the second technique's more of the variation of parameters that's coming up is more of a Betty Crocker, do this, do this, do this type method, so you can follow through better step by step. This technique, though, is a better technique when it works. It's faster and there's no integration in it. It's just subbing and some differentiation. So it is a better technique if you can use it, but it requires a little bit of practice on your part to figure out what's a good guess. So there's a second video on this unknown coefficients that I guess you can take a look at after this one, which is now.